Lesson 8, Quinn, I called this cool applications, and they are. Unfortunately, with spring break just around the corner and me wanting to give you time to study, I'm going to skip some of the cool applications because I'm not going to be testing you on them, and I want to give you time to work on stuff. But I have to look at roller coasters. So here is the physics of a roller coaster loop. And if I do my job right, you will learn that what you thought of as roller coaster loops is totally wrong. A roller coaster barely makes it around a vertical loop of radius 4 meters. A says, find the minimum height that the roller coaster needs to start from the top of the hill. And then part B says, find the normal force or the apparent weight of a passenger when the coaster returns to the bottom of the loop.
That kind of sounds like something from earlier in here.
Pardon me?
Kind of sounds like something from earlier in
except I very carefully avoided loops because it turns out the physics of a loop is going to be quite surprising but kind of cool. So I guess in part A, what we want to find is that. Okay. I'm going to call this, and can you label it? I'm going to call this location here initial. And final for part A, I want to be actually the top of the loop, and you'll see why in a second. Hey Jake, is there a change in height in this question? Is there a change in speed in this question? Is there a yucky curvy path in this question? Folks, you know what this is a job for? Conservation of energy. Okay? So I'm going to start out KE initial plus PE initial equals KE final plus PE final. Are any of these 0? We're going to start out at rest. Are we starting out on the ground at the initial location? No. Are we coming to a stop at the top of the loop? That would be a problem. Did I say at the top of the loop? So that's not 0 either. Okay. Are we on the Earth? So I can use MGH. I don't need to use the cosmic one. Oh, thank God. So my next line, I'm going to go MGH initial equals a half MV final squared plus MGH final. Hey, Mac. Masses cancel. Will an empty roller coaster make it through this loop as well as a full roller coaster? Yes. And again, I should say, in real life, friction actually makes it so the masses don't cancel. But if you grease it down and make friction as small as possible, you can make it fairly negligible. Okay. What are we trying to find? Let's come back to that for a second. Let's walk through. I want to get height initial. Do I know G? Yeah. Do I know the final height? Yeah, 8, I think. Do I know G? When the 4 is the radius. So 8, final height would be 8, right? Right? Yeah. Do I know G? Do I know how fast I'm traveling up there? Wait a minute. At the top, what path am I tracing out? And the circle equation had a V in it quite often, didn't it? Let's try analyzing the top with a free body diagram and circles. At the top, what are the forces acting on this roller coaster? Get the obvious one. What else? Oh, and am I on the Earth? Yes. So I can use, thank God, mg. I don't have to use big G, big M, little m over, right? What else? Normal force, which way? Which way is this person's head pointing? So normal force, also down. What path is this person tracing out? A circle. So which way must my net winning force be pointing? Toward the center. Who's winning? It's kind of a trick question. Both are. They both are. I get this. mg and plus the normal force equals, and I'm going to go with m. I'm going to put the v squared over r because I'm pretty sure I'd like to find v. Okay. What word did I underline? You're right. I did that deliberately. What we're saying is you almost feel like you're going to fall out of the roller coaster. If you feel like you're going to fall out of the roller coaster, yeah. Question or?
Yeah, question.
Yeah.
I've been a little bit confused. How
Yeah.
do you know when to put it mv squared over r and when to just put v squared over r? Because I noticed.
Well, no. Is this a force?
Yeah.
Is this a force?
Yeah.
Force equals mass times acceleration. All that is acceleration.
Okay.
So don't tell me force equals acceleration. That's why. Now, once in a while, if we've been able to cancel out m's, maybe that's what you're remembering. But when we're doing a force equation, when we're doing winner minus loser, don't forget the m in front of the a. And also the other one is the 4 pi squared r over t squared. That's an acceleration. Put an m in front of it. Great question. I'm glad you asked that. Coming back to, what did you say, Jake? Barely? What I'm saying then is you feel like you're going to fall out. You're screaming, which would not be a popular ride, but we're doing bare minimum right now. What I'm really saying, Riley, is we're going to go so slow. If you feel like you're going to fall out, what we're really saying, Quinn, is you don't feel any normal force. In fact, what we really get is this. Now Colin, the m's cancel. And so this is also leading to why you're wondering, well, how come sometimes it's there, sometimes not? What do I want to get by itself here? Actually, I'm going to be really clever. I think I'm going to get v squared by itself. Because isn't there a v squared there? Well, why not do that? So I get this. I get v squared equals ger. Is that right? So what can I replace the v squared with? All right, so I get this. G h initial, and what we want to find is my initial minimum height, equals a half ger plus g, and then stop. Don't write h final. Look up. How far from here to here, what do I call that? As a letter? How far from here to here? How far from here to here? How far from here to here? How far is the height in terms of r? 2r. Yeah? Let's do that. Mac, do you notice something weird about this equation? You don't? What cancels? Huh? What cancels? What this is saying, Jake, is this roller coaster would work on any planet in the universe with this height. The speed would be different on Jupiter or on the moon or on Mars, but I'm telling you, the coaster would make it safely through the loop. When little g cancels, what that's saying is, it doesn't matter which planet you put it on. With me so far? So the final height, the minimum safe height, equals, now what do I have left? I have 0.5 r plus 2r. Oh, I can do that in my head. What's 0.5 r plus 2r? I love this one. And I'm not saying I like this question. I'm just saying I love the fact that you get such a clean answer. If you want to build a roller coaster with a circular loop, your hill has to be at least 2.5 times the radius of the loop. I'm willing to bet ride designers that would be one of the things that they would have memorized out of laziness, the same way we all know that G is 9.8. Now, I'm also going to tell you, no one builds roller coasters this way for 2 reasons. First of all, barely making it, you would feel like you were falling out. You would scream in terror. But there's another reason. The very, very first roller coasters that were built with loops weren't actually roller coasters. I think the first one was built, I think around 1920 at Coney Island. All it was a long ramp with a loop at the bottom. And it was hugely popular. but they had to station ambulances permanently at the bottom. People regularly blacked out. People regularly had nosebleeds. They had permanent nurses down there. Why? Oh, first of all, before we go on to part B, it's going to be 2.5. What is the actual radius of this question? You know what? I'll bet you can do that in your head. 2.5 times 4 is? It turns out you'd have to have a hill 10 meters high. Okay? The real issue is, at the bottom of this coaster, the normal force is quite extraordinary. Oh, and by the way, we're doing bare minimum. In real life, they would have a lot of extra velocity for safety. So in real life, the number that we're about to calculate for part B would be far larger if you built it this way. What does part B want me to find? The normal force at the bottom. Yes? Okay. I'm going to call this location B, both for bottom and for part B. What are the forces acting on the bottom? Get the obvious one. mg down. What else? Normal force, which way? Up. Bigger, smaller, or the same size as mg? What path is this thing tracing out? A circle. Okay. So at the bottom, we have this. Normal force minus mg equals, and again, Colin, it'll be mv squared over r. How would I get the normal force by itself? Okay, so the normal force is going to be mg plus mv squared over r, or mv squared over r plus mg. Mass does not cancel this time, by the way. A heavier person would feel this much more than a lighter person. Oh, that makes sense, because a heavier person feels heavier. Duh. Okay. Double check, do I know the mass? I think I said 50 or something. Do I know g? Yep. Do I know the mass? Yep. Do I know r? Yep. Do I know how fast we're traveling at the bottom? That's at the top. Gerd's at the top. But you know what? Cade, is there a change in height? Is there a change in speed? Is there a yucky curvy path? I think I can solve this one straight with conservation of energy, because really what I want is the velocity right here, which will be the velocity right there. Is that okay? So I think I can go KE initial plus PE initial equals KE final plus PE final. Are any of these zero? Well, yeah, we're starting at rest. Oh, and where is location B? On the... Hey, I can cancel out potential energy final. It's kind of nice. I'm going to get mgh initial equals a half mv final squared. And instead of v final, if you want to, you can change that f into a capital B, v bottom squared. That's really what I'm talking about, right? Hey, Mac, do the masses cancel here? Excuse me. Yeah? No yawning. How would I get the... Oh, wait a minute. I was going to get the v by itself, but Mac, is there a v squared here again? I'm going to cleverly just get the v squared by itself. How would I do that? Oh, put a 2 there. So what can I replace the v at the bottom squared with? A 2gh initial. Is that okay? What can I replace v at the bottom squared with? A 2g... Wait. 2.5 r. Wasn't that my initial height, algebraically? This is for Cade. Cade, what's 2 times 2.5? What's g times r, Cade? I know you want to say it. Hey, there you go. So you actually get 5 ger. I can replace the v squared with a 5 ger. Okay? I got to move below here, but hopefully you have room. The normal force is going to be mg plus m5 ger over r. Oh! Kind of cool. I have mg plus 5 mg. What is 1 mg plus 5 mg? If you're building this roller coaster, the person at the bottom is going to be pulling 6 Gs at the bottom of the loop. That is well beyond what people are comfortable with. Oh, and sorry, that's bare minimum. You're barely making it through the loop. If you build any kind of a safety margin by having the first hill higher so that they hit the bottom of the loop faster, they're going to be pulling 8 or 9 Gs. And when you get to 11 Gs, you're blacking out, you're causing nosebleeds, you're having real issues.
Wait a minute, Mr. Dewick, I've been on a roller coaster with a loop, and I didn't black out.
That's because nobody builds circular loops nowadays. Okay? So a little nerd trivia, you don't need to write this part down, but as a physics nerd, nowadays what we build are what are called clothoid loops. And a clothoid loop is shaped like a teardrop, like that. Not a circle. And it turns out that allows you to have a way smaller speed coming in, and it has a way smaller normal force at the bottom, and it gives you, because of the tighter turn at the top, a bigger normal force at the top, which means you have a bigger safety margin because you don't need to go as fast to have a bigger normal force so that people feel safe. How many of you have been to California Screaming in Disney? Okay. You've been on the roller coaster? Okay. If you look at that loop, it looks nearly circular. Now, it's not. I'm telling you, it's not. It's a very, very extended clothoid loop. If you go through that loop on all the roller coasters that I've been on, that's the one where I do feel the G-forces the most at the bottom. That's the one I always hold my hands out at the bottom and try and lift my arms up while I'm at the bottom. You can't. You can't. Or the other one I'll do sometimes is I'll tilt my head forward, and when I get to the bottom of the roller coaster, I'll try and lift my neck up. You can't. You can't. And that's because it's certainly, it's not a circle. It's not. But it's a fairly circular clothoid loop. Okay. So this was why the very first shoot the chute ramp, people were blacking out. People were getting nosebleeds because this would be bare minimum. I assure you, they were going faster than bare minimum, and they were pulling way more than that. But loops are cool. I grew up in the pre-video game generation, so I played with toys. Yeah, I did. And for little boys growing up, the toys that we had a big box of, we had Hot Wheels cars. And one of the all-time great inventions was those plastic orange race tracks that you could stitch together, and they came with, what did they come with? A loop, right? This is the physics of that. Wonder if you could build one of those in real life. Put your pencils down. Okay. So just to clarify, not on your test. Although when we do our Playland Physics field trip, I think one of the handouts where it looks at loops might talk about that a bit. Example 2. A toy plane is attached to a ceiling via a string. Has a propeller which causes it to move in a circle as seen below in side view. If we ignore air resistance and the force from the propeller, which of the following is the best force diagram for the plane? A, B, or C? I think we can figure this out. This is a job for a free body diagram. What are the forces acting on this plane? Get the obvious one. I agree. By the way, you've seen these little toys, right? Outside stores, they have them all the time. They're going around. We call this, where it's going at an angle, we call it a conical pendulum. It's a pendulum because it is a mass attached to a string. It's a conical pendulum because it's tracing out a cone, conical cone. Okay. This is the physics of the wave swinger at Playland, the swing sets that you go on that go around and have the music. Okay, basically the same idea there. Also, the atmosphere is a conical pendulum as well. So what are the forces acting on? Oh, And I said, so the plane has a propeller pulling it forwards, air resistance slowing it down. So in terms of its speed, it's constant. Its acceleration is changing the direction. What are the forces acting on it? Get the obvious one, mg. What else? Is there a rope? Tension. Believe it or not, that's it. C is correct. Wait a minute, Mr. Dewick. You said that what path is this plane tracing out? A circle. So where must my net force be pointing? Toward the center. I don't, well, do I have two forces in this picture, Colin? Say yes.
Yes.
Are they at angles?
Yes.
What if I wanted to add them together? How might I choose to add those two vectors together? Draw them. So if I do that, I get this. Gravity down, right? Tension. And you can see, oh, look at that. There is the resultant, and my net force is pointing directly toward the center. You only need those two forces, and that'll pull you in a circle. Okay? Explain why the others are wrong. Right there. That's all you need. This also brings us to a question from, I think, last class? 2 classes ago, lesson 6, Mr. Dewick. Yeah. Just look up and you can follow along. Number 13, why is it that a plane has to tilt its wings in order to turn? I don't know if you've been in an airplane, but they don't turn level. They have to tilt. Why do they do that? That's a lot of work. Coffee can spill. Passengers feel a little. Why wouldn't you just stay level and turn? Well, on a plane, the free body diagram is gravity down and lift. If I have two forces vertical, is there any way that I can end up with a force pointing towards the center of a circle? But if here, now I have two forces at angles. When I tilt the plane, lift is at an angle. Colin, how would I add those two forces together? I get this. Gravity. I get lift. And lo and behold, that's what gives me a net force pointing towards the center. That's why planes have to tilt in order to turn. Who knew? But in hindsight, cool. I would love to do example 3. This is where I'm going to cut corners. I've kind of talked about it a little bit, but I'm going to pass it. I'm going to skip example 4. It's cool. I'm going to skip example 5. It's cool. Going to skip example 6, although it's cool. Okay?
Is any of that on the test?
No, that's why I'm skipping it. Please, if it was on the test, I'd be covering it, but I've rewritten the test. I'm not putting a conical pendulum on your test. I'd like to, but I'm not going to. Okay? So we're going to finish off with example 7. Example 7. Ty, what does A want me to find? Big M. Well, they gave me its gravitational potential energy. They gave me its orbital radius. You know what? I'm going to try starting with the gravitational potential energy. I know that gravitational potential energy is negative big G, big M, little m over R. Which are in this case? I think in this case are orb, because I think that's what they gave me the energy at level at. What did you say they wanted me to find? Big M. Did they give me the potential energy in the question? Yeah? G, I know, 6.67. Do I know little m? Yeah? Do I know the radius of the orbit? Oh, hey, I can find the mass of the planet. How? I think it's going to be the mass equals R times the potential energy divided by big G little m. Is that right? That would move to there. Those would move down. Oh, but there's going to be a negative kicking around. Or, Mac, I could say this. Ty, what are we trying to find? Which is what? Mass. I could just say, I know the answer is positive because it's mass, and I could just ignore all the negatives kicking through. But anyways, okay, let's try this. Big M is going to be negative R 8.85 times 10 to the 6th. PE negative 6.55 times 10 to the 10th. All over 6.67 times 10 to the negative 11. Little m, 965. Negative 8.85 times 10 to the 6th times negative, I get a negative times a negative, which is a positive, which is good because mass is a scalar. It better be a positive. Divided by bracket 6.67 times 10 to the negative 11 times 965. And I get that. Times 10 to the? Oh, and you know what? I think Earth is 10 to the 24th. So you know what? I'm okay with this. This seems like a planet-ish thing. I'm going to, because I know I'm going to use this, I'm going to write 9.006, because it's 598 times 10 to the 24th. I'm going to write 9.006 times 10 to the 24th, and then I'm going to write 9 times 10 to the 24th kilograms. Although Mr. Duick says go to 2 or 3 sig figs, I'll go 9.0. You know what? It's about 1.5 times the mass of the Earth, because the Earth is 5.986 times 10 to the 24th, 9 times 10 to the 24th, a little bigger than Earth. If you were on this planet, probably you'd feel a little heavier because it would be exerting a slightly larger force of gravity on you. Probably. What does B want me to find? Quinn, what does B want me to find when you're done yawning? You know what? I think it wants me to find V orb, which I think was big square root big G big M over R orb. Is that right? I'm going from memory. This was the one where we said,
Gravity is what's pulling me.
in a circle. We derived it. Are we okay with that? I'm cutting corners just to save time, but you guys are good with that one? All right. It's going to be the square root of 6.67 times 10 to the negative 11. Big M, 9.006 times 10 to the 24th. All over the radius, 8.85 times 10 to the 6th. .67 times 10 to the negative 11 times, answer button, divided by 8.85 times 10 to the 6th. Oh, square root. And that seems about right. Most of our orbital velocities were in the 1,000 or 10,000-ish range anyways, right? So 8,240 meters per second. Jose, what does C want me to find? Well, that hasn't changed. Which V? I guess orb. Right? Which M? Little m. So it's going to be 0.5 times 965 times, I'm going to write 8,240 squared, but I'm going to use my answer button if that's okay with you. So I'm going to go 0.5 times 965 times answer button squared. Look at that. 3.275 times 10 to the 10th. There was a quicker way to do this. This C. Handy shortcut. Can someone on your calculator, or all of you on your calculator, type in the potential energy, which was 6, but leave it positive. Type in this number here, the 6.55 times 10 to the 10th. Type in this number here, 6.55 times 10 to the 10th. Just leave off the negative. And go divided by 2. What do you get? Do you remember at the end of lesson 6, in part of lesson 7, I said, for what it's worth, again, you can survive fine without it, Devin, because I got the answer without it, but I said, if you want a neat shortcut, turns out if you're in orbit, your kinetic energy is the same as half of your potential energy there, but positive. Oh, and I also said your total energy there is the same as your kinetic energy, but negative. In other words, and if you don't believe me, the word total means add the potential and the kinetic, and you'll get that. Which, again, Lewis, means you really didn't need that shortcut, because total means add. You could have just added them together. It's a meh kind of a shortcut. Okay. What's your homework? I'm going to give you a roller coaster question, number 2. Number 2 wants you to find the normal force at the very, very top. So in this case, the normal force won't be 0, but you can start out using the same approach. Just don't cross out the Fn, get the Fn by itself. 4 is good. Eight is good. Cool. Skip. I know what I'm looking for here, Mr. Dewick. I think I know what I'm looking for here, Mr. Dewick. Skip. 17. You can finish the quiz, and you can now do every question on the ultimate review. I got one more cool video to show you.